More than 1,000 years ago, somewhere in the Maya world, specialists were watching the sky and recording the movement of the moon. They had no telescopes, computers, precision clocks, or modern astronomical instruments, yet they were studying one of the most dramatic events visible from Earth, a solar eclipse. And new research suggests their system was far more sophisticated than simply recording when an eclipse had happened. The Maya appear to have developed a method that could keep eclipse predictions useful across generations. The evidence survives inside one of the rarest books from the pre-Columbian Americas, the Dresden Codex. It is an accordion-folded Maya manuscript filled with numbers, ritual calendars, gods, astronomical observations, and mathematical calculations. Among its pages is a section that researchers have studied for more than a century, the Maya eclipse table. For years, scholars understood that the table was connected to cycles of the moon and to periods when eclipses could occur. But there was still an important question. How could the Maya continue using such a table without its predictions slowly becoming inaccurate? A new study by anthropologists John Justison and Justin Lowry offers an explanation. Their reconstruction suggests that Maya astronomers were not simply reaching the end of one eclipse table and starting again from the beginning. Instead, they may have deliberately restarted their calculations at carefully chosen points before the old table was finished. To understand why this matters, we first have to understand what the Dresden eclipse table actually contains. The table covers 405 lunar months, a period of about 32 3/4 years. In the Maya calculation, those 405 lunar months correspond to 11,960 days. That number is especially interesting because it also equals exactly 46 cycles of the Maya 260-day ritual calendar. So the movements of the moon and the sacred calendar could return to alignment within the same mathematical system. But the real difficulty with predicting eclipses is that the moon does not behave according to perfectly neat calendar numbers. The moon orbits Earth, while Earth orbits the sun, and the moon's orbit is tilted relative to Earth's path around the sun. That is why we do not experience a solar eclipse every month. Most of the time, the moon passes slightly above or below the sun from our perspective on Earth. Only when the moon passes near specific points in its orbit at the right time can an eclipse occur. Modern astronomy calls those crossing points lunar nodes. The Maya did not need modern orbital physics to notice that eclipses followed repeating patterns. They needed long-term observation, accurate records, and the ability to recognize cycles hidden inside those observations. And that is exactly what the Dresden Codex appears to preserve. According to the new reconstruction, 2 points in the table were particularly important: 223 lunar months and 358 lunar months. The number 223 is immediately recognizable to modern astronomers. 223 lunar months are approximately equal to the Saros cycle, one of the best-known eclipse cycles in astronomy. After roughly 223 lunations, the positions of the Sun, Earth, and Moon become similar enough for another eclipse to occur. The Maya could not have known the modern gravitational explanation behind this pattern. But they could observe that eclipses returned according to a repeating rhythm. The 358-month interval may have been even more useful for maintaining the accuracy of their particular eclipse table. Justison and Lowry proposed that instead of allowing the entire 405-month sequence to repeat continuously, Maya specialists could restart the system after 358 months. Doing this kept the predicted eclipse seasons closely aligned with the actual movements of the moon. But even this correction was not perfect forever. Small errors would still accumulate over long periods of time. So the Maya system appears to contain another level of correction. 4 periods of 358 lunar months combined with 1 period of 223 lunar months equal 1,655 lunar months. That is almost 134 years. Across that enormous span of time, The researchers calculate that the average accumulated displacement could remain less than about 51 minutes. That is remarkable because it means the system was not designed for a single astronomer or even a single generation. The people who created these calculations understood that astronomical knowledge had to survive beyond one human lifetime. One generation could observe the sky, another could inherit the calculations, another could correct them, and another could continue the same system decades later. The eclipse table was therefore not simply a list of dates. It functioned more like an astronomical model that could be renewed when necessary. The researchers also studied historical eclipses visible from Maya territory over many centuries. Their reconstruction indicates that versions of this method could have anticipated the solar eclipses visible in the Maya region throughout the relevant sequences. The surviving Dresden eclipse table probably represented a 32 3/4 year period beginning around either 1083 or 1116. But the astronomical tradition behind it appears to be much older. Maya inscriptions containing detailed lunar information already existed centuries before the surviving Dresden Codex was produced. The researchers suggest that eclipse tables related to this system may have existed by around the middle of the 6th century. If that interpretation is correct, the surviving manuscript may represent the result of hundreds of years of observation and refinement. Another unusual feature of the table reveals how carefully the Maya organized the information. There are 69 marked lunar positions within the sequence. But researchers identify only 55 as positions associated with genuine opportunities for solar eclipses. The remaining positions appear to have helped preserve the mathematical structure of the table. They created a regular sequence in which important positions were separated by intervals of 5 or 6 lunar months. This is important because it shows that the Maya were not simply writing down eclipses they had already witnessed. They were constructing a framework for identifying when future eclipses were possible. The precision of their lunar calculations is equally impressive. One mathematical relationship examined in the research uses 1,447 days for 49 lunar months. Divide 1,447 by 49 and the result is approximately 29.530612 days for the average lunar month. The modern value is approximately 29.530589 days. The difference is only around 2 seconds per lunar month. Researchers cannot prove that every Maya astronomer used exactly this formula in exactly the same way. But the calculation demonstrates how accurately Maya mathematics could represent the real lunar cycle. And all of this was accomplished without telescopes, digital sensors, computers, or modern physics. Their most important instrument was time. Night after night they could observe where the moon appeared, how its shape changed, and how long it took to return to the same phase. Over years, patterns became visible. Across generations, those patterns could be measured more precisely. And when the predictions began to drift away from reality, the calculations could be corrected. That ability to recognize accumulated error may be one of the most important parts of the entire system. Discovering a repeating cycle is impressive. Discovering that your own mathematical model slowly loses accuracy and then developing a method to correct it shows a much deeper understanding. For the Maya, however, astronomy was not separated from religion, politics, and ritual in the way modern science often is. The movements of the sun, moon, planets, and stars were connected with gods, calendars, ceremonies, rulers, and ideas about the structure of the universe. A solar eclipse would have been an especially powerful event. In the middle of the day, the sun could begin to disappear. Light would weaken, the temperature could fall, and the familiar appearance of the sky could suddenly change. If Maya specialists knew that such an event was possible before it occurred, that knowledge would have carried enormous authority. Ritual preparations could be made, political meaning could be attached to the event, and the specialists responsible for maintaining the calendar would appear capable of understanding the behavior of the heavens. Imagine being told that the sun might soon darken. Then, on the expected day, you watch a black shape slowly begin moving across it. For someone without knowledge of modern astronomy, the experience would have been extraordinary. And the people who had studied the calendar would appear to have known that it was coming. Unfortunately, only a tiny part of the Maya written tradition survives today. During the Spanish conquest and colonial period, many Maya books were destroyed. We do not know how many astronomical manuscripts once existed or how much knowledge disappeared with them. The Dresden Codex is therefore not necessarily an isolated achievement. It may simply be one surviving fragment of a much larger intellectual tradition. Today the manuscript is preserved in Dresden, Germany, thousands of kilometers from the civilization that created it. Its pages are damaged and some interpretations remain debated. But the numbers are still there. And centuries after the manuscript was written, researchers are still discovering new ways to understand them. The most remarkable part of the story may not be that the Maya possessed some mysterious or impossible knowledge. Their achievement can be explained through something much more powerful: careful observation repeated over extraordinary periods of time. They watched, they recorded, they counted, they compared the results, and they passed the information forward. Eventually, those observations became a mathematical system accurate enough to identify when the sun itself might disappear. The Dresden Codex is therefore more than an ancient manuscript filled with strange symbols and numbers. It is evidence of a scientific tradition built across generations. A tradition capable not only of recognizing patterns in the sky, but also of recognizing imperfections in its own predictions. And perhaps that is the real discovery hidden inside these pages. The Maya were not simply repeating ancient calculations. They appear to have been refining them, testing them against reality, correcting them when necessary, and preserving those corrections for people who would continue the work long after they were gone. More than 1,000 years later, those numbers are still revealing just how closely the Maya learned to read the sky. This is Veloris, because the truth is rarely on the surface.